First of all, I would like to thank the organizers for inviting me to this nice conference, and well, the audience for showing up. This is work in collaboration with Lars Andersson and Peter Blue. You have heard both of them during this conference. Part of this is published in this article in Classical and Quantum Gravity, but parts of it we have not published yet. First, just going to tell what I mean with a symmetry operator. And for me, a symmetry operator is a linear differential operator that maps a solution of some field equation to, or generally differential equation to a new solution. Well, it could be the same solution, it doesn't matter. We do this with a clear motivation that we want to use this to construct higher order energy momentum tensors and conserved currents and things like that, and use them for decay estimates. So we have a clear goal in mind here. I will use spinor notation throughout. Lars has told you both in the course and in his talk a little bit about what it is, but I'm going just very quickly to recap the similarities and differences between ordinary tensor notation. The tensors, you have four-dimensional real vector bundles because we are just studying a four-dimensional manifold. But for the spinors here, I'm going to use the two-dimensional complex spin bundles. Abstract indices like, well, A then becomes a pair of indices A and A prime. And of course also on the covariant derivative we also get two indices, even though it's still just a first order operator. The metric for the tensors is symmetric, but the metric for the spinors is antisymmetric, and that makes actually quite a big change in how to handle the algebra. There is also a correspondence between the totally symmetric spinors and the symmetric and trace-free tensors. So you actually automatically get the trace-free property if you have the symmetry property. This is just a simple example. We have two numbers for the valence. So valence 3, 2 has 3 unprimed and 2 primed indices. One very important thing to handle the algebra in a nice way is what I call irreducible decompositions. This is partly based in the following argument. So, the spin bundle is just two-dimensional. Therefore we only get one-dimensional space of antisymmetric valence 2 series spinors. The spin metric is such a spinor, so therefore it spans this space. And then if we apply this to the following idea, so I hardly see this dot. So if we begin with just any spinor with two indices, then we can split that into a symmetric and an antisymmetric part. That's very easy, and that can always be done. But now this antisymmetric part is actually proportional to the spin metric. And the proportionality factor just becomes a trace like this. This is of course a bit more complicated in general, but you can still follow the same procedure and get, for instance, the composition of a 3-index spinor, and actually any spinor can be decomposed in this way. And this is what I call an irreducible decomposition. The very nice thing here is that we only need to work now with symmetric spinors and the spin metric. I have actually implemented this in this computer algebra package sim manipulator, which I've written, and it is for the exact suit for Mathematica. I can actually recommend that for many abstract calculations and, well, a few concrete too. But this is quite nice. And now, because we are only dealing with symmetric spinors, it also makes sense to split the covariant derivative of a symmetric spinor into these irreducible parts. Lars told you a little bit about this, but he didn't go into any detail. So this is how it works for, well, example of a 3-2 spinor. So we get these 4 different parts. The divergence we can define like this. So we have two index contractions. The curl and the curl dagger have 1 index contraction, and then we symmetrize over the remaining indices. And the twistor operator, or, well, sometimes we can shorten it to twist. I don't know if that is a good name though, but well, all names are not good. We just symmetrize over all indices. So this gives us all these irreducible parts. It's quite obvious how this plot generalizes, but also this formula in the top generalizes to arbitrary spinors, but we just need these coefficients to know what these are, and I have a formula for that too. To interpret these things, we can just look at very simple examples which we know about for ordinary tensors. So just on a scalar we can only form the gradient, and, well, this is the twistor operator here. For one forms, or equivalently 1-1 spinors, we have the divergence, and then the curl and curl dagger are actually the anti-self-dual and the self-dual parts of the exterior derivative. So we not only split into, well, forms and things like that, but we also split with according to self-duality and anti-self-duality. The twistor operator here is just a conformal killing vector operator. And actually all these operators have nice conformal behavior, but they do have different conformal weights, all 3 of them. For the trace-free symmetric 2 tensor, we certainly have the divergence, of course, and the twistor operator is a conformal killing tensor operator. I didn't take the curl and curl dagger here. Of course we have them, but the interpretation is not as simple. One of the more important classes of spinors is spinors in the kernel of this twistor operator, and we call them killing spinors of valence KL. And of course, clear examples, the conformal killing vector, so valence 1-1, trace-free valence 2 conformal killing tensor is valence 2-2 case. But another very important case for us is the valence 2 serial killing spinor. It's not immediate on how you translate that into tensor. You actually have to multiply with a spin metric to get the right number of indices. But if you do that, then you get an anti-self-dual conformal killing nanotensor. Well, it's a bit of a mouthful. Now when we know our operators, we can actually start to study field equations. And I'm mainly interested in the Maxwell equation here. But we'll look a bit into the conformal wave equation and the Dirac Weyl equation. And they can be very neatly formulated just in terms of these curl-dagger operators. Well, this is quite familiar in the standard form. The special thing here is that if you take a complex conjugate of for instance, the Maxwell equation, then you just get curl-dagger of curl of phi bar. So these equations actually comes in complex conjugated pairs. So now if we study symmetry operators, we can do two different things. Either we map a solution to the Maxwell equation to a solution to the Maxwell equation, or a solution to the Maxwell equation to the complex conjugated version. And the Dirac Weyl works the same way. Actually, higher spin also has exactly the same formula, but they don't make as much sense in a curved spacetime, because we are going to study this on a fairly arbitrary curved spacetime. We'll see what the conditions are for existence of these kind of symmetry operators. But we'll mainly concentrate on this first kind of symmetry operators, where we just map solution of this curl-dagger equation to the curl-dagger equation. Just to introduce a little bit more notation here, all these symmetry operators I'm going to talk about here will require existence of a killing spinor. And if we have a killing spinor, we can actually form these two slightly weird expressions just involving the curvature, Weyl curvature, and here the trace-free Ricci. And these will soon be clear what we use them for. If we are going to study just symmetry operators for the conformal wave equation, we just have to look in the literature and find results from people in the audience. And just to see how this fits into the general picture here, I have translated it to this setting. And to have a symmetry operator a second order symmetry operator for a solution to the conformal wave equation like this, then we need this L, which is just a trace-free conformal killing tensor, or valence 2 killing spinor, a valence 1 killing spinor. This means a conformal killing vector, and then we need this scalar, so that the gradient of this scalar is actually just matches this O0 operator, which I defined here. The interesting thing is now when we go to the Dirac Weyl equation, we get an almost identical system. But the difference here is, we still have the valence 2 killing spinor, but now instead of 0 here, we get this other, the O1 operator. And this last equation looks almost identical. I mean, we have different coefficients here, but that doesn't really matter much. There. For the Maxwell equation, we also get a very similar system. But now instead where is this? Yeah. The last equation simplifies. So this Q just have to be a constant. Now when we have seen that we have such similarities between all the cases, we can actually formulate now two conditions. Of course we have a condition that we should have a valence 2 killing spinor. But if we do have that, that might not be enough. So we have this condition A0 and A1. The A0 is that we should have a scalar so that the gradient of the scalar just matches the O0 operator. I mean, 0 here is for the spin 0 case, and 1 is for the spin 1 case. And for the condition A1, we need a vector field which satisfies this. So we take the conformal killing vector operator, and that should match the O1 operator. So in just one picture we get this. So for all these operators we certainly need a valence 2-2 killing spinor. And if we have well, for a conformal wave equation we need the condition A0. For the Maxwell equation we need a condition A1, and for the Dirac Weyl we actually need both. And so I think that is a quite new thing to see, that we actually get the same conditions for well, we need both the conditions for the Maxwell equation and for the conformal wave equation to get the symmetry operator for the Dirac Weyl, which is kind of neat. The most interesting question now is, of course, do we have any sensible solutions to these obstructions? And yes, we do. The simplest is if you just take two conformal killing vectors and construct the product like this, then we can actually find these these P's and Q's. So we solve both of these conditions. I didn't write out formula for it, but it only contains psi and theta and derivatives of them. But that is quite standard thing. The slightly nicer or slightly more interesting case here is if we take a valence 2-0 killing spinor and just take the product of that and its complex conjugate, then we still get a valence 2-2 killing spinor, and we can find the corresponding P's and Q's, so we get solutions to both of these conditions. We actually even have a counterexample, well, an example of a valence 2-2 killing spinor which does not satisfy the A0 condition, but it does satisfy the A1 condition. It would be nice to have a counterexample for the A1 condition too, but it might be difficult to find. Now, for the rest of the talk, I will concentrate on the Maxwell equation because, well, we will use that as a good model problem for the linearized gravity, which is the next step, but we have not gone that far yet. And also the Maxwell case is slightly neater than the Dirac Weyl case, for instance. So in this case, the symmetry operator can actually be written in this very nice form, where A here is constructed from the L and the P, and the Q just needed to be a constant. So this is of course quite obvious. If you take your old solution, multiply it with a constant, then yeah, you get a solution. That's quite clear. So that part is not very interesting, but it is nice to see that we actually get a potential. A is a potential for the Maxwell field, so we automatically get that. It's also noteworthy to see that the chiral dagger of A is 0, and this link will be used a bit later, and actually this, the form 1 here, is the general form of a first order operator which satisfies this, well, you can add a gradient of a scalar that you form from phi 2. But apart from that, it is the general form. Now, what does this operator look like if we just take a product of conformal killing vectors? Well, then it becomes a quite simple thing. We just take Lie derivatives, well, actually a conformally weighted Lie derivative here, which is defined in this way for this spin. If you have other spins, you get yet another term here. And the potential also has a very nice form. But here we see that we can split it up into first order operators. So this is not a particularly exciting case. This case, however, when we form it from a valence to steric killing spinor, is well, a bit more surprising perhaps. But we can still get a quite nice form. So we have this nice potential form, and the potential here just comes, well, it's a first order expression. And the nice thing here is that it just formed from this theta, which is a contraction between the killing spinor and the field. And if you remember a little bit of what Lars said, we can find a nice principal null dyad, and in that dyad kappa should be, well, omicron iota, which means that this expression does not depend on the middle component of the Maxwell field. It only depends on the extreme scalars. So this, for instance, is not at all sensitive to the Coulomb solutions. But I mean, in general, this operator, even though it's a second order, it will not split up as two first order symmetry operators after each other. And because of that, we call it a hidden symmetry, because it's not generated by, well, killing vector fields or conformal killing vector fields. And then, of course, what we are most interested in is the Kerr spacetime, and it does admit this particular symmetry operator. Now we can go over to study conserved currents, and we'll soon see the link between these. And for me, a conserved current is just a fancy name of a divergence-free vector field. And of course, we want to inform this from a Maxwell field. Otherwise, it does not have any connection with the field we are studying. And there is a special class of these conserved currents, which are the so-called trivial currents. And in my notation, this just means that they come from a curl and a curl dagger of some spinors. If we want to look at this as fluxes through hypersurfaces, then if we have this, if we have a trivial current, then we'll only get contribution from the boundary of this hypersurface, and so therefore they are of less importance in some sense, and we'll only study, in a sense, equivalence classes of currents up to trivial currents. So one particularly interesting class of currents is if you want J to be, well, divergence-free, of course, and formed as a differential operator which is bilinear in the field and its complex conjugate. So it has form phi times phi bar, but you can have derivatives wherever you want. Then, after doing some integration by parts, in some sense, you can actually move over all derivatives to one side, so to say. So you get this form, where now J tilde is a trivial current. And of course, phi is a Maxwell field. So if you just want this to be divergence free, then you see that A must satisfy this curl-dagger equation. So this is a kind of a joint equation for the Maxwell equation, and this is a quite nice equation too. And if we just have this and take curl of A, then we can actually see that we get the symmetry operator again. And if we go back a few slides, oops, sorry, no, that was too many slides. Here, we see that at least for a second order symmetry operator, we did get this potential form. And we have only proven that for second order, so we don't know if that holds for higher order, but it's very unlikely that it would not hold. But the point here is that this A, well, in the symmetry operators, really matches the A we have in the current here. And we actually had this general form of a first order A which satisfies this. So there is the link between symmetry operators of second order and currents of first order. Now we can look at very simple examples. Yeah, and I should get again this general form. The simplest case we can think of here is, of course, if we just let L be 0 and let P be a conformal killing vector, or, well, even a killing vector, why not? And then we just get A to be a, well, contraction between the killing vector and the field. If we form this current, then we just get this, which was not so surprising perhaps, because this is just the standard energy momentum tensor contracted with a killing vector field. So this is, of course, very well known, and it's a very standard way of constructing it. Now, if we take this form, but plug in a symmetry operator here instead, so we do like this. We have chi here with a second order symmetry operator we can take. Then we still get that this A satisfies the curl-dagger equation, so we get the conserved current. And it, well, it will look like that first term. It does not change anything if we take the complex conjugate of that. So we get the second term, and summing them will, of course, still get a conserved current. But the important thing here is to see that, well, now we have another kind of energy momentum tensor, but it's a polarized energy momentum tensor. So we have two derivatives on the first factor and no derivatives on the second factor, which is not very good because we would like to have some positivity, some dominant energy condition, something. So if we, if we want to do estimates, we really need to have some nice sign. So non-negativity, if we contract with future pointing time like vector field, is certainly useful for that purpose. And if we do that with this first current, it is a very standard result, and it's not very difficult to prove that this indeed becomes non-negative, because we can actually write this out as a sum of squares of components. This second current here, well, J1, here we cannot even hope for that, because we have two different kinds of objects multiplied with each other. So we need to do some kind of integration by parts to get one derivative over to the other side. Let us now take the simplest example of a second order symmetry operator we can, and just take this the same killing vector as we had. So we just take these two lead derivatives. Then we can actually take this J1 and move a symmetry operator over to the other side. Well, a lead derivative over to the other side. So we get this, and this trivial current we have to add just looks like this. I mean, the form of that is not particularly important, but we just get a trivial current from these two last terms. And now this first part is just like the standard energy momentum tensor, but we have a lead derivative first. So this certainly has the same positivity properties. So that's nice. But now, if we look at the Kerr spacetime and try to do something similar with a hidden symmetry, we'll see what happens. So just to see a little bit of how these things work in Kerr, I introduce even more notation, of course. In Kerr, we can build basically everything from this valence 2 zero killing spinor we have. So we can build psi here, which will be killing vector, and it will actually be the DDT killing vector field if we normalize kappa in the right way. We have the theta, which I described before, which just contains the extreme components of the field. We also define now an eta, which is curl dagger of this theta. And so this is just a first order expression in the field. And now if we just plug this into the previous equations we had, we get that the symmetry operator has this nice potential form with the potential just described in terms of this theta and the eta. So that's simple. Now if we try to do this integration by parts, then we can, here we had zero derivatives, two derivatives. Now we move them over, so we get this v here. And we can actually get eta times eta bar. So this is first order times first order. And then unfortunately we get also these lower order things, which is zeroth order times first order. But the really nice thing here is that these two first terms look very much like the energy momentum tensor for a scalar field. And we do have this first order times first order and nice quadratic-like expression. So we actually get a dominance property of these two first terms, and then we have some lower order stuff which we need to handle, but we can actually handle that. And it's actually slightly surprising that we actually get psi, well, the killing vector contracted with a tensor like this. Yep. The trivial current here, the form of that is not particularly important, but we do get that. But if we look at the properties of this V, we see a few different things. First of all, if we compute the divergence of this, it's actually 0, which is really nice and a bit surprising. It's also symmetric. And if we take a killing vector field and a time-like vector field, well, and let's say that xi is also time-like, then we get positivity. So we actually have dominance properties of these first-order terms, but we need to add a little bit of some lower-order energy to control these lower-order terms, but that can actually be done. So if we sum all this up, we see that we can actually use this V as a new energy momentum tensor for the Maxwell field. And this is of first order times first order. So it is very similar to the standard energy momentum tensor for a scalar field, which is quite different from the standard one for the Maxwell field. So we certainly have similarities between this new energy momentum tensor and the one for the scalar field. The algebraic structure looks very similar. It has a non-vanishing trace, and this is actually quite useful when we do integrated decay estimates, because that's part of what fails if we try to do these estimates just for the standard Maxwell energy. So this is very good. Then if we look, it just depends on, basically just depends on eta and theta, and if we just look at the definition, we see here that theta does not depend on the middle component, so eta does not either. And then here we only have Lie derivatives. So we see that the Coulomb solution will not show up in the theta or eta. And of course, if we take Lie derivative along a time-like killing vector field of the Coulomb solution, we don't get anything either. So it's not sensitive at all to the Coulomb solution. And that can be very helpful if we don't. So this means that we might not need to subtract a particular Coulomb solution from the solution when we try to study the decay estimates. And we have done some work this far, mainly for Schwarzschild case on this, and these integrated decay estimates seem to work for that case. And for the Kerr case, we are still working on it, and the algebra is quite complicated, but hopefully we'll get something out of that very soon. It's still work in progress. So, well, I do have quite a lot of time, so I think I'm just going to a little bit about how you can actually find, well, how you can actually prove, let's say, this, that the general form of a symmetry operator for the Maxwell field just is this, and especially how you get these conditions. And that was almost large and lost. So there are a few observations we need to make. Well, first of all, we just take a Maxwell field. And then by this irreducible decomposition of the covariant derivative, we see that we get the twistor operator, and then, well, the curl cannot be formed and the divergence cannot be formed, so we don't get these terms. We could form the curl dagger, but that is zero because of Maxwell equation. So we actually get this identity. So all first order derivatives can be expressed in terms of just this twistor operator. And also higher order derivatives. Well, we can get the twist, but all the other ones we can actually reduce to lower order things by using some commutators. I have formulated commutators for all these operators. So we can always reduce everything down to just involve the twistor operator on all on the field. So therefore we can make an ansatz like this. If we just want a general second order differential operator, which should be linear, acting on a Maxwell field, then it must look something like this. Well, if we want two indices left. Then the general procedure is to do irreducible decomposition of these things. We'll have some symmetries. I mean, AB will be symmetric, and then this is completely symmetric, so we have some symmetries here. But I mean, it will be a bit of a mess, but that can be done. And the same thing for M and N. When we have done this, we can just plug this into the Maxwell equation. So we look at this equation, which now will be a third order thing. Quite long, unfortunately. But still, because we only have 3 derivatives, so therefore we should be able to write it in terms of these 3 twistor operators on the field. And of course, lower order things, so 2 derivatives, 1 derivative, and no derivatives on the field. So we get all these 4 parts, and of course some perhaps lengthy expression for these coefficients. But well, we have this nice property of the Maxwell equation that it forms an exact set of fields according to Penrose's definition, which means that we at a point can prescribe these derivatives, but just at a point. And this means that they should be really independent. So these coefficients in front should vanish. So that these are the equations we get. So we actually get, well, in a sense, 4 equations, which we can decompose and set all these to 0. That gives us a huge system, which we then, after by using a lot of commutators and simplifying steps, can reduce down to this, in a sense, very simple set of equations we have here. So we're actually just left with this quite neat set of equations. Well, I think that's all I'm going to say, unless you have questions.